This is SpaceTime, Series 22, Episode 27. Coming up on SpaceTime: discovery of galaxies without dark matter, the Earth confirmed as a less volatile version of the Sun, and new evidence of deep groundwater on the red planet Mars. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
Astronomers have discovered two galaxies which appear to contain little or no dark matter. The findings, reported in the astrophysical journal Letters, could provide new clues about the very nature of dark matter. Dark matter is a mysterious, invisible substance thought to dominate the makeup of galaxies. In fact, scientists know dark matter exists because of its gravitational influence on galaxies. Trouble is, they have no idea what dark matter is, but they can estimate it makes up about 85% of all the matter in the universe. So, finding an object like a galaxy missing dark matter is unprecedented, and it's come as a complete surprise. Astronomers first detected a galaxy, NGC 1052-DF2, about 2 years ago. Their calculations quickly showed this galaxy lacked dark matter. But because it was the first and only time anyone had seen such a thing, the authors couldn't help but wonder whether or not they were wrong, whether or not they had somehow missed something important. The study's lead author, Peter Van Dokkum from Yale University, says the new observations confirm the original data. Better still, they also found a second galaxy also lacking dark matter. The authors used the giant 10-meter Keck telescope in Hawaii to gather their new, more precise measurements for DF2, confirming that globular clusters inside the galaxy were moving at a speed consistent with the mass of the galaxy's normal matter only. If there was dark matter in DF2, the clusters should be moving much faster. But then the authors found another galaxy, NGC 1052-DF4, which was also devoid of dark matter. Van Dokkum says this second discovery means the chances of finding more of these galaxies is now much higher than previously thought. Right now, astronomers don't have any good ideas as to how these galaxies could have formed. Like DF2, DF4 belongs to a relatively new class of galaxies called ultra-diffuse galaxies. These galaxies are every bit as large as the Milky Way, but have between 100 and 1,000 times fewer stars, making them appear very fluffy and translucent, therefore difficult to observe. Ironically, the lack of dark matter in these ultra-diffuse galaxies actually strengthens the dark matter theory. That's because it proves that dark matter is a real substance that's not coupled to normal matter, as this proves both can now be found separately. I'm Stuart Gary. You're listening to SpaceTime. A new study has confirmed that the Earth is made out of the same elements as the Sun, but has less of the volatile elements, such as hydrogen, helium, oxygen, and nitrogen. The findings, reported in the journal Icarus and on the pre-press physics website archive.org, are part of a new project designed to measure the elemental composition of other stars and the terrestrial exoplanets orbiting around them. One of the study's authors, Associate Professor Charlie Lineweaver from the Australian National University, says the composition of a rocky planet is one of the most important missing pieces in science's efforts to determine if a planet is habitable. Lineweaver says every star has some kind of planetary system in orbit around it, and the majority of stars probably have rocky planets in or near their habitable zones. That is the Goldilocks area around a star where it's not too hot and not too cold but just right for liquid water, essential for life as we know it, to pool on the surface. And just like the Earth, other terrestrial worlds are also devolatilized pieces of their host stars. You see, stars and the planets orbiting around them form at the same time through the same gravitational collapse of a molecular gas and dust cloud. The centers of these molecular clouds are cold, dark and dense, containing hundreds to millions of times the mass of the Sun. The collapse can be triggered by a range of events, including overdensities caused by gravitational interactions with large bodies or structures, by black holes, or by shock waves from nearby supernovae, as was the case for the formation of the Sun and its solar system of planets, moons, asteroids, comets and meteoroids 4.6 billion years ago. As gravity pulls material in the collapsing cloud closer together, the center of the cloud gets more and more compressed and hotter. Depending on the mass of the collapsing molecular cloud, hundreds to thousands of hot overdense regions can form, each with the potential to become the core of a newborn star. As the molecular cloud continues to collapse, it fragments into smaller superdense regions, which eventually further contract to each form a protostellar core. Around each of these protostellar cores, inherent motions within the collapsing cloud causes the cloud to churn and begin rotating in the same direction. The protostar continues to accrete material from the surrounding stellar nebula, increasing in density and mass and therefore gravity, which causes further contraction. The conservation of angular momentum produced by the spinning protostar's contraction causes it to increase its rotation rate, while at the same time the ongoing accretion of surrounding material causes its core pressure and temperature to further increase. Eventually, the core pressure and temperature of the contracting protostar increases to the point where nuclear fusion begins, as hydrogen atoms are forced together, forming helium atoms, releasing huge amounts of energy in the process, and the newborn star begins to shine. For about 90% of its life, the star will continue to burn hydrogen into helium, a period in its evolution known as the main sequence. Meanwhile, at the same time as all this is happening at the center, the rotating cloud surrounding the protostar begins to flatten out into a disk and gets thinner and thinner as it spins, sort of like a spinning clump of dough flattening out into the shape of a pizza. These circumstellar or protoplanetary disks, as they're called, are the birthplaces of planets. As the disk spins, the material within it travels around the star in the same direction. Eventually, the tiny grains of material within the disk will begin sticking together due to electrostatic charges. As these small clumps of material orbit within the disk, they gradually accrete more and more of the surrounding material, growing bigger and bigger in the process. And the bigger these conglomerates become, the more gravity they have, and so the more material they attract, and the bigger they get. Eventually, they form planetesimals, which themselves can then grow big enough to become planets. Different materials condense out of the protoplanetary disk at different distances from the protostar, depending on temperature. Metals such as iron, nickel and aluminum, together with rocky materials such as silicon, will condense out closer to the star than volatile compounds such as water, ammonia, methane, carbon dioxide and carbon monoxide, which can condense out into solid ice grains beyond the so-called snow line. Therefore, the inner regions of these circumstellar or protoplanetary disks usually contain mostly rocky material, as much of the original gas is likely being gobbled up and cleared out by the developing star. All this leads to the formation of smaller rocky planetesimals close into the star. In the outer part of the disk, though, more gas remains, as well as ices that haven't been vaporized by the growing star. This additional material allows planetesimals further out from the star to gather more material, eventually evolving into gas and ice giants. The authors conducted their study by comparing the composition of Earth rocks with meteorites and with the Sun's outer atmosphere. This comparison yields a wealth of information about the way the Earth formed. Lineweaver says there's a remarkably linear volatility trend that can be used as a baseline to understand the relationships between meteorites, planets, and stellar compositions.
You know, by looking at the spectra of stars, that we can tell the abundances of elements in other stars. And now you also know that recently that we found statistically that every star that you can see has some type of planetary system. Now, we don't know that for sure. We can't detect them directly because our sensitivity is not good enough, but we know enough about our sensitivity to know that, yes, that is consistent with all these stars having rocky planets of some kind. So then the step is, well, are they like Earth? What are they made of? What is their chemical composition? Well, we know the chemical composition of their host stars. Can we use that to infer the chemical composition of their rocky planets? And I think the answer is yes. In other words, the devolatilization that happens to a protoplanetary disk is probably a universal feature. Helium is light everywhere in the universe. So that's basically the idea. Since we know the composition of stars, we can get a good estimate of what the compositions of their rocky Earth-like planets are around them. So to do that, you say, well, how are we going to calibrate this? Well, let's calibrate it by figuring out exactly what the Earth is made of and exactly what the Sun is made of. Now, you'd say, well, isn't that already known? And the answer is, not really, or kind of. And so 2 years ago, when we started this project, we said, well, I guess the first thing we have to do is figure out what the Earth is made of. And then we spent about 1.5 years looking at the various estimates of the elemental composition of the Earth, how much carbon, how much oxygen, how much silicon, etc. And when we did this, we found that 95% of the effort has gone into figuring out what the mantle of the Earth is, but not what the bulk of the Earth is. So this is why it took us a long time to get the best estimate for the composition of the bulk Earth, the whole Earth, and for various reasons. And the main problem with The previous estimates were they didn't have error bars. Now, as a physicist, I can't imagine doing science without error bars, but a large fraction of the literature on the composition of the Earth did not have error bars on them. And I say, well, without error bars, we can't do anything. We can't compare the Earth to the Sun. If you don't have error bars on your data, you can't see whether the data is consistent or not with itself. So we wrote a paper a year and a half ago on what is the composition of the Earth with uncertainties. So
I remember
since
interviewing you on it at the time.
Right. So, but that was one step in the path towards comparing the Earth and the Sun's compositions. So once we had the Earth with error bars, we then took the trouble to say, okay, now let's update the composition of the Sun, making sure we have error bars, making sure we're using all available data and the updated data. We did that, and then we put on one plot the Earth and the Sun in a more detailed way with error bars than anyone has done before. I'm very proud of this. I always kid my earth science colleagues about we have an astrophysicist telling them what the Earth is made of. And so what we did was we had the best Earth, we had the best Sun, and now we could make the best comparison of the two. Now that gave us lots of insights into how the Earth was made. So, for example, we normalized all the elements to the Sun's elements, and then we plotted the abundances of the Earth, and you can see that the Earth's elements, for all the what are refractory things, so the non-volatile things like calcium and aluminum, these are things that you heat up and they just sit there. All those are the same. The relative abundances of those elements in the Sun and the Earth are the same. But for the volatile elements, like carbon and oxygen, helium and hydrogen, those have been depleted. And the interesting thing is that they've been depleted in a way on a log-log plot that's linear. And no one has quantified that linearity better than we have. And the cool thing there is you have a line and then it becomes horizontal, and there's a kink. And that kink we call the devolatilization temperature of the Earth. And crudely speaking, this temperature of 1,391 plus or minus 15 Kelvin is the best estimate ever made for this devolatilization temperature, which, roughly speaking, can be interpreted as the highest temperature that the material that went into forming the Earth was ever experienced.
Does that tell us something about where the Earth was built?
A little bit, but not as much as we'd like, because the reason for that is that the luminosity of the Sun has changed over time. It goes down, its luminosity decreases as it approaches the Hayashi track. That takes about 50 or 80 million years, and during that 50 and 80 million years are what is the period of called oligarchic growth, and that's where a lot of this devolatilization occurs, we think. So by making this devolatilization the most accurate quantification of devolatilization, we then say, okay, let's take that same pattern, and let's assume that it has happened elsewhere around other stars at about 1 AU, or at about the luminosity appropriate for rocky planets, which depends. It's kind of like the habitable zone. Let's just say habitable zone devolatilization. And then that's what we have, a potentially universal pattern of devolatilization that produces rocky planets around stars everywhere in the universe. That's the main big, this paper that we just published is a calibrator for that type of extrapolation to other planetary systems.
And that gives you an ability to determine whether or not a planet in the habitable zone would have the sort of elements necessary for life to exist, such as we have here on Earth.
Well, I'd like to agree with that, but because we do not know the range of elemental abundances that are compatible with habitability, we're not that far yet.
Okay.
But yes. Okay. If we knew what life was and the range of life and the range of chemical abundances which were consistent with life, then the answer to your question would be yes.
That's Associate Professor Charlie Lineweaver from the Australian National University. And this is Space Time. I'm Stuart Gary. A new study claims liquid water could still be present at multiple locations deep below the Martian surface. The new findings, reported in the journal Nature Geoscience, follows research published last year showing the detection of a deep water lake below the red planet's south polar ice cap. Mars was once a warm, wet world with a thick atmosphere. Even today, Mars is covered with geological evidence showing vast quantities of liquid water once flowed over its surface. Satellite observations have identified dry stream beds, river deltas, the shorelines of lakes, and the basin of a giant northern hemisphere ocean, complete with beaches and islands. Ground-based chemical analyses of Martian surface material has identified minerals which could only have been formed in liquid water. However, as the red planet's core cooled and solidified, its geodynamo stopped, shutting down the Martian magnetic field. Magnetic fields are important because they help protect a planet's atmosphere, shielding the surface from irradiation and helping prevent the solar wind from eroding the atmosphere into space. Without its magnetic field, the Martian atmosphere was gradually ripped off the planet and degassed into space. Eventually, the atmospheric pressure dropped to the point where water could no longer remain liquid on the surface. This new study suggests that deep groundwater could still be active on Mars and could be producing surface streams near some equatorial areas. The authors believe their studies show active systems as deep as 750 meters from which groundwater works its way to the surface through cracks. Their findings are based on features on the red planet's surface known as recurring slope lineae, dark streaks running down the sides of slopes and crater walls which appear in warmer seasons and then disappear again in cooler ones. Scientists have hypothesized that these features could be water runoff from subsurface permafrost. However, some satellite observations have suggested this could just be mineral movement. The authors of this new study propose the streaks are water, but not from melted permafrost just below the surface. Instead, originating from deep pressurized groundwater sources, which work their way to the surface moving up through cracks. Their hypothesis is based on research in desert hydrology, after the authors saw similar mechanisms in subsurface aquifers and groundwater flow movement in the northern African Sahara and on the Arabian Peninsula. Previous research to explore groundwater on Mars relied on interpreting the returned electromagnetic echoes sent from radar probing experiments aboard the Mars Express and Mars Reconnaissance Orbiter spacecraft. However, other than the 2018 South Pole detection, none of these have provided any evidence of groundwater occurrence. The authors of this current study instead used high-resolution optical imaging and modelling to study the walls of the large impact craters on Mars, correlating known impact fractures with the sources of recurring slope lineae. The authors claim that pressurized deep groundwater then worked its way up through the cracks to become the source of the recurring slope lineae's water. I'm Stuart Gary. This is SpaceTime. Israel's Beresheet or Genesis lunar lander has successfully carried out one of its most crucial engine firings. The 60-second-long burn was designed to further expand the spacecraft's orbit, increasing its apogee or most distant point from the Earth to also encompass the Moon. Using orbital raising instead of a direct lunar transfer maneuver has become the preferred method for reaching the Moon for robotic missions. That's because it uses less fuel. On the downside, it takes a lot longer, 7 weeks rather than just 3 days. So what does all this mean? Well, Genesis is now on a trajectory into an elliptical orbit, expanding to some 405,000 kilometers from Earth. The maneuver allows mission managers to optimize the spacecraft's trajectory for lunar capture and orbit insertion on April the 4th. SpaceIL Chief Ofer Doran says mission managers are now preparing to perform a series of small maneuvers in order to optimize the spacecraft's trajectory for lunar capture.
So today at 2:30 in the afternoon, we performed another successful maneuver for Beresheet. We raised our apogee, the furthest part of our trajectory, to about 405,000 kilometers. That's enough to reach the distance of the Moon from the Earth, and it's actually our last maneuver to get closer to the Moon. We will have a couple of more maneuvers over the following days that are small maneuvers to slightly adjust our trajectory, but we are on the way to the Moon very successfully right now. It was a good maneuver. We operated our main engine for about 60 seconds. All the systems functioned as expected. We've learned to deal with the difficulties we've been having with the star trackers and what that entails in maneuvering the spacecraft in a non-nominal fashion. So that was working quite well today. We were lucky to have the engine firing in a communication pass. We actually saw it in real time and didn't have to wait biting our fingernails until we saw results 15 minutes later, like last time. So a successful maneuver, good work by the engineering teams of SpaceIL and IAI, and we are on the way to meeting the Moon.
That's Ofer Doran, the head of SpaceIL. Now, if all continues on track, Genesis will touch down in the northeastern plain of a giant lunar basin known as the Mare Serenitatis, or Sea of Serenity. The touchdown will make Israel only the fourth nation on Earth after the Soviet Union, the United States, and China to land a spacecraft on the lunar surface. The 674-kilometer wide Sea of Serenity basin is a vast basaltic lava floodplain. It was created by volcanic eruptions, and it appears dark to those observing the Moon from Earth, which is why ancient sky watchers describe these lava basins as seas. The landing site's only a few hundred kilometers east of the 1971 Apollo 15 landing site, and a similar distance northwest of the 1972 Apollo 17 landing site. Once on the lunar surface, Genesis will send back images and use its magnetometer to study the lunar magnetic field, helping scientists better understand how the moon formed. It'll also deploy a laser retroreflector array on the lunar surface for NASA as part of a new lunar-based navigation system. If the timing's right, NASA's Lunar Reconnaissance Orbiter will be on hand to document the spacecraft's descent and landing. The 585-kilogram Genesis lunar lander blasted into orbit back on February the 22nd aboard a SpaceX Falcon 9 rocket from Space Launch Complex 40 at the Cape Canaveral Air Force Station in Florida. The mission comes 50 years after America's historic Apollo 11 lunar landing, when Neil Armstrong and Buzz Aldrin became the first men to walk on the moon. And time now to take a brief look at some of the other stories making news in science this week with a science report. A new study says rising temperatures from climate change are predicted to increase the threat to the exposure of mosquito-borne diseases. The warning reported in the journal PLOS, Neglected Tropical Diseases, suggests the worst climate change scenarios will see more disease brought by mozzies in Europe, but the burden will lessen in Southeast Asia and West Africa. Surprisingly, they predict middle-of-the-road temperature increases could actually produce the highest expansion of disease transmission from mosquitoes. A new study claims shift work increases a person's risk of developing heart disease by about 1% every year. The findings, reported in the journal Occupational Medicine, are based on data from over 320,000 people with over 19,000 cases of heart disease. Researchers found that shift workers who work irregular hours, evening work or night work, were 13% more likely to develop heart disease compared to daytime workers. And while the exact reason for this remains unknown, the study provides evidence that shift work should be reduced as much as possible, and employers should pay more attention to the health of their staff. A new study has found that teens who believe everything happens by chance are far more likely to become smokers or risky drinkers than their counterparts who believe they have control over their own actions. The findings, reported in one of the journals of the Royal Society, are based on data from over 4,600 young people across the United Kingdom. Researchers found that teens who believed events happened by chance at age 16 were more likely to be smoking and drinking alcohol by the age of 17. Researchers from the Australian National University have discovered several new species of butterflies and moths in northern Australia, identifying what they describe as a conservation stronghold of both national and international significance. Among the discoveries were a breeding colony of a rare species of whistling moth not seen for 110 years and known only by a single museum specimen collected back in 1878. Researchers have also been able to expunge 10 species from the record, either erroneously described or mistaken for another species. The findings are the culmination of more than 10 years of research in a largely unstudied area comprising the Kimberley region of northwestern Australia, the top end and northern deserts of the Northern Territory, and the western Gulf country of Queensland. 35% of the butterfly and moth fauna in the area is endemic to the region and found nowhere else in the world. Western Australian scientists have discovered two enzymes that help explain the sensitivity of wheat plants to salty soils. The findings, reported in the journal New Phytologist, could lead to advances that help strengthen crops against salinity, an issue costing farmers more than $500 million a year. An improved understanding of the effects of salinity on crops at a molecular level is essential for developing more tolerant wheat varieties, allowing farmers to reclaim land currently too saline for wheat crops. Well, we all know that a bad night's sleep can make people a little bit, shall we say, touchy, but the reasons exactly why people get cranky with not enough sleep are still somewhat unclear. Now, a report in one of the journals of the Royal Society has been able to rule out at least one more possible cause. Scientists now know crankiness from a lack of sleep is not being caused by reduced brain activity. 47 people aged 20 to 30 and a further 33 aged 65 to 75 were deliberately given a terrible night's sleep, then asked to perform a series of tasks while their brains were being scanned. The participants had more trouble regulating their emotions because of the lack of sleep. But the scan showed the problems weren't associated with the prefrontal cortex or amygdala, the decision-making and emotional areas of the brain. The findings were not what researchers had expected, and it means scientists will simply need to dig a lot deeper in order to figure out why people get grumpy when they don't get enough sleep. Okay, let's start this story by stating categorically the Earth is an oblate spheroid. This is a fact, there is no doubt. Conspiracy theorists who believe the Earth is flat have announced plans for an expedition to the edge of the world in order to try and prove there actually is an edge. The flat earthers plan to travel to Antarctica to find a 50-metre tall ice wall barrier which they believe is guarded by NASA and which they're sure marks the edge of the world. Flat earthers believe Antarctica goes all the way around the flat Earth, forming a sort of border to stop you falling off the edge. Of course, carrying out an expedition to prove the Earth is flat raises all sorts of questions about navigation. You see, with a flat Earth, there could be no magnetic North Pole, because the geodynamo that generates the planet's magnetic field couldn't exist, and so compasses wouldn't work. For that matter, nor would GPS satellites, which after all are orbiting a spherical planet. So all that means is the flat earthers will actually have no way of finding the Antarctic. Of course, if the Earth really was flat, all those hundreds of thousands of images taken from space showing a curved Earth would all have to be faked. And there are heaps of other problems with the idea of a flat Earth too. The centre of gravity would be at different locations, depending where you were standing. Lunar eclipses could only ever occur at midnight. Different countries couldn't experience different seasons at different times. Different stars wouldn't be visible at different latitudes. Ships sailing away wouldn't disappear over the horizon. They just get smaller and smaller. And the horizon itself wouldn't be further away the higher up you are. Sunsets and sunrises couldn't happen at different times. And identical sticks placed vertically in the ground at different places many kilometres apart couldn't cast different shadows. Flat earthers tend to be marginalised individuals, looking for ways to dismiss inconvenient truths, who don't understand science and almost certainly believe in other conspiracy theories as well. It gives them a feeling of privileged knowledge that others don't have, allowing them to feel special and more important than they really are. Tim Mendham from Australian Skeptics says Associate Professor Steve Novella from The Skeptic's Guide to the Universe has now written about what drives flat earthers on his blog Neurologica.
This is a weird thing. I mean, the sort of flat earth movement has resurfaced. The flat earth movement's been around a long time, obviously. I have to say up front, no one in the old days, ancient days, believed the earth was flat. The earth was always round. They knew it back in ancient Greek times, etc., etc., etc.
Well, they proved it in ancient Greek times, yes.
That's right. Ptolemy, who was a big... he knew it was round. They all knew it was round. Columbus knew it was round. Everyone knew it was round. There wasn't this sort of fear of falling off. It comes and goes. And the fact that this belief goes against every bit of scientific knowledge it's easily ripped down and debunked through a lot of evidence, mountains of evidence to say it's rubbish. It still sits there. And you wonder why people are believing it. And one is that people don't believe in authority. They worry about authority telling them things, so they go the opposite way. Two, there are people who are just ignorant of science and who, even though you supply a lot of evidence to them, they still won't listen because they have a confirmation bias. They'll hear what they want to hear. And three, I think there's a lot of people having a laugh, quite frankly. It is a joke. You sit there and scratch your head and crash your forehead against your desk, etc. when you hear people seriously believing this stuff. I think most of them are not serious. It's just a fun thing to do, a fun, wacky thing to do. But yeah, Steve's written a very good article about it, quite lengthy article about that. You can just look it up under Neurologica, which is his blog, Neurologica, and just look up there under Flat Earthers. And it's a pretty good article, very much worthwhile having a look at.
That's Tim Mendham from Australian Skeptics. And of course, if you need any further proof that the Earth is not flat, remember, if it really was flat, cats would have pushed everything off the edge by now. You're listening to Space Time. I'm Stuart Gary, and that's the show for now. You can subscribe and download Space Time as a free twice-weekly podcast through Apple Podcast iTunes, Stitcher, Bytes.com, Pocket Casts, SoundCloud, YouTube, Audio Boom, from spacetimewithstuartgary.com, or from your favourite podcast download provider. Spacetime's also broadcast coast to coast across the United States on Science 360 Radio by the National Science Foundation in Washington, D.C., and available around the world on TuneIn Radio. If you want more Spacetime, check out our blog where you'll find all the stuff we couldn't fit in the show, as well as loads of images, news stories, videos, and things on the web I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word and in lowercase, and that's Tumblr without the E. You can also follow us on Twitter through @StuartGary, at Spacetime with Stuart Gary on Instagram, and on Facebook, just go to www.facebook.com/Spacetime with Stuart Gary. Spacetime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe.
You've been listening to Spacetime with Stuart Gary. This has been another quality podcast production from Bytes.com.